9.5 Lesson 2, Alternating Series. We have one objective for today. You'll be able to approximate the sum of a convergent alternating series. So if we know that we have a convergent alternating series, it must converge to some sum. So it's an infinite sum, but it has a finite value. So how can we approximate the value of this sum, this infinite sum? Well, we can use a partial sum. We can use an nth partial sum as an approximation for the infinite sum. But how do we know how good our approximation is? There is something called the alternating series remainder theorem that will let us know how close our approximation is to the actual sum. And this will, so we will know the maximum possible error of our approximation. Just like I said, this theorem will let us know how close our approximation is to the actual sum. So we're going to be looking at something called the alternating series remainder theorem. So here we're going to take a look at the alternating series remainder theorem, Theorem 9.15, and it states the following. If a convergent alternating series satisfies the condition that the n plus 1th term is less than or equal to the nth term, then the absolute value of the remainder r sub n, what is this remainder r sub n? Then the absolute value of the remainder r sub n involved in approximating the sum of the series, the infinite sum, by an nth partial sum, that difference between the exact sum of the infinite series and our approximation for it, called the nth partial sum, the absolute value of that difference is called the absolute value of the nth remainder. And according to this theorem, the alternating series remainder theorem, that is going to be less than or equal to the first neglected term. So how do we know what the first neglected term is? It is a sub n plus 1. So here we have the sum of the first n terms of our alternating series, designated s sub n, the nth partial sum. And this theorem states that the difference between the infinite sum and the nth partial sum, the absolute value of that difference will be less than or equal to the first neglected term. We will come back and briefly look at the proof a little bit later, but I think it would be helpful for you to see exactly what this theorem is stating by looking at an example. So here we have example 4, approximating the sum of an alternating series. So the instructions are, approximate the sum of the following alternating series by finding its 6th partial sum. So we have an infinite alternating series from the first term going all the way to infinity. And here we have the rule for our series. The nth term is given by negative 1 to the n plus 1, which is of course responsible for the alternation of signs. And then we have 1 over n factorial. N goes from 1 to infinity. So we have an infinite alternating series. How do we know that it converges? You can verify using the alternating series test that we learned yesterday. So all you're checking for are two conditions. You can check that the limit of a sub n, which is 1 over n factorial, as n goes to infinity is equal to 0, and it is, because as n goes to infinity, n factorial will go to infinity, so 1 over n factorial will go to 0. And you can also check that a sub n plus 1 is less than or equal to a sub n for all n. Alright, so we can check that a sub n plus 1 is less than or equal to a sub n for all n greater than or equal to 1 or greater than or equal to some integer. So we can verify that very quickly. A sub n plus 1 will be 1 over n plus 1 factorial, and that's got to be less than or equal to 1 over n factorial. Is that true? The numerators are the same, so the fraction with the larger denominator will be smaller. And of course, n plus 1 factorial is larger than n factorial. So we do have a convergent alternating series. I verified that. And look at Theorem 9.15, the alternating series remainder theorem. It states if a convergent alternating series satisfies this condition, and it does, we verified that, then the absolute value of the remainder r sub n involved in approximating the infinite sum by an nth partial sum is less than or equal to the first neglected term. So this infinite sum has some value. We know that because this alternating series converges. So it converges to a finite value. The infinite sum has a finite value. But what is that finite value? What is that infinite sum? We can approximate the infinite sum by adding the first n terms to get an nth partial sum. And in this particular problem, it states approximate the infinite sum of this convergent alternating series by its first 6 terms. In other words, by finding its 6th partial sum. So how do we find the 6th partial sum? We just add these 6 terms. 1, 2, 3, 4, 5, and 6. But of course, that's not the infinite series, because the infinite series has infinitely many terms. So, but we can approximate the infinite sum with our 6th partial sum. So the infinite sum is approximately equal to the 6th partial sum. But how good will our approximation be? How close will our approximation be to the exact infinite sum? The alternating series remainder theorem tells us that the difference between the infinite sum and our nth partial sum, the absolute value of that difference, will be less than or equal to the first neglected term. So in our particular example, for example 4, we have this. We have S representing the infinite sum of this convergent alternating series, and the difference between that and our 6th partial sum approximation, the absolute value of that difference will be less than or equal to the first neglected term. So the first neglected term will be the 7th term. 6 plus 1 is 7. So that's all that states. So what is the 7th term? And what do you look at from the nth term? You only look at the unsigned part of it. You don't look at the negative 1 to the n plus 1. You're just looking at the 1 over n factorial. So according to the alternating series remainder theorem, the difference between the infinite sum and our 6th partial sum approximation for it, the absolute value of that difference, will be less than or equal to the first neglected term. So you look at this, 1 over n factorial, n is 7, so 1 over 7 factorial. So in other words, we're not going to be off from the actual infinite sum by any more than this amount. That's what the alternating series remainder tells us. It tells us how good our approximation will be for an infinite sum for a convergent alternating series. So looking further at what we have here for example 4, it's explaining what we just went over. So the series converges by the alternating series test. We checked that earlier in our work. The sum of the first 6 terms, called the 6th partial sum. If you use your calculator, you will be able to get a decimal value for that 6th partial sum. It is about 0.63194. And the alternating series remainder theorem tells us that the difference between our sixth partial sum and the exact infinite sum will be less than or equal to the first neglected term, which is 1 over 7 factorial, or 1 over 7 factorial is 5040, which is approximately 0.0002. So the infinite sum what is the infinite sum? Well, here is our approximation for it. And now we know that the infinite sum will differ from our approximation by an amount that's no greater than the first neglected term. So using that, we can state what is stated in the last sentence for the example. Let's take a look at that. So what we have here is an absolute value inequality. We can rewrite that as a compound inequality, and then we can isolate the infinite sum by adding the sixth partial sum to each of the three parts of our compound inequality. And when we do that, the last line is what we get. So we know what the sixth partial sum is. It's this value. And we know what the seventh term is. It is this value. So our last compound inequality states that the infinite sum will be somewhere between the sixth partial sum minus the maximum possible error and the sixth partial sum plus the maximum possible error. And that's what we have right here. Here's the sixth partial sum minus the maximum possible error. Here's the sixth partial sum plus the maximum possible error. So the infinite sum will be somewhere between those two values. And that's what we're able to do by using the alternating series remainder theorem. Now we take a look at number 44, which is another variation in applying the alternating series remainder theorem. So this is another type of problem that you could do with the alternating series remainder theorem. So the instructions for number 44 are to use the alternating series remainder theorem to determine the number of terms required. So in the previous example, we approximated the infinite sum with the sixth partial sum because we were told to do that. And then we figured out how much our approximation could be off from the exact sum by using the alternating series remainder theorem. But in this problem, we're not told to use the sixth partial sum. In fact, we're being asked to determine what partial sum we should use, because it says determine the number of terms required to approximate the infinite sum of the convergent alternating series with an acceptable error that has to be less than 1,000. So in the previous problem, we were told to use the sixth partial sum, and then we were asked to figure out how off our approximation could be. In this problem, we are told that our approximation should not be off from the exact infinite sum by more than 1,000th. And then we have to figure out what partial sum will accomplish that for us. So it's a different type of application, but we're using the same theorem. So how do we do this? Let's review the alternating series remainder theorem once again. It states if a convergent alternating series satisfies this condition, then the absolute value of the remainder R sub n in approximating the infinite sum by an nth partial sum is less than or equal to the first neglected term. And that's what you need to focus on. So whatever partial sum you're using, the difference between the nth partial sum and the infinite sum, the absolute value of that difference, has to be less than or equal to the first neglected term. So it really comes down to this. You want to know what is the first term in our series whose 1 over n squared value will be less than 1,000th. If we can figure out what term from our series will have a value that's less than 1,000th, then we will know that we need to add all of the terms before that. So And why is that? Because of the alternating series remainder theorem, which states that the difference between the nth partial sum and the infinite sum, the absolute value of that difference, has to be less than or equal to the first neglected term. Now that we understand what we're supposed to do, the question then becomes, how do we do it? How do we figure out the first term of our series that is less than 1,000th? You can use a graphing calculator or Desmos, an online graphing calculator, and all you're going to do is enter the rule that you see here for a sub n, which is 1 over n squared. You can also enter 1 over x squared, that's fine, and just make a table and see what the values are for different values of n, starting at n is equal to 1 and going up by 1 each time. And then keep going until you find a value for 1 over n squared that's less than 1,000th, and then you have to add all of the terms before that. So let's take a look at that using Desmos. So go to desmos.com or use your graphing calculator, and all you have to do is enter 1 over x squared. I'm using the variable x, but remember you have 1 over n squared, so n has to be a positive integer starting at 1. Well, that's okay. I just click on the table function in Desmos and I get a table, and I can just enter values like 1 and 2 and press enter each time, and it will automatically go to the next integer value. So after you enter 1 and 2, you can just keep pressing enter again and again and again, and it will automatically take you to the next value following the pattern from your first two values. The pattern from our first two values is that they are integers and they differ by 1. So when you press enter each time, you just get the next and next and next integer value. So you're finding values of 1 over n squared for different values of n. And remember, our objective is to find the first value of 1 over n squared that is less than 1,000th. So by the time you get to n is equal to 10, the value is 100th, right? Still more than 1,000th, so we have to keep going. So you can see that I went further and further. By the time we get to the 20th term, it is still more than 1,000th. It's about 2,000ths, somewhere between 2,000ths and 3,000ths. By the time we get to the 29th term, it's slightly more than 1,000th. Not much more, but slightly more than 1,000th. So we're getting pretty close, but we need to keep going. And then you can see here, by the time we get to the 31st term, it's still more than 1,000th, but not much more. So you can see 0.001, but it's still greater than 1,000th because you have all of that. But what happens when you get to the 32nd term? It's going to be, you have the number here written in scientific notation. So if you write it as a decimal, you'll have 0. And you can see that that number here is less than 1,000th. That is less than 0.001. 0.001 is greater than that value. So what does that mean? So you should add the first 31 terms of our convergent alternating series. So what that means is you need to find the 31st partial sum, because according to the alternating series remainder theorem, the difference between the infinite sum and the 31st partial sum, the absolute value of that difference will be less than or equal to the first neglected term, which would be the 32nd term. And from our table, we know that the 32nd term is going to be less than 0.001. So when you look at this inequality that we have here, this compound inequality, here's what we can see. We can see when you just look at the part here and this part here that we will have the difference between the infinite sum and the 31th partial sum. The absolute value of that difference will be less than 1,000th. So by applying the alternating series remainder theorem in this way, we're able to determine that we need to find the 31st partial sum to approximate the sum of our convergent alternating series with an error that's less than the acceptable 1,000th margin. So to conclude, we just write what we found. We need to find the 31st partial sum to approximate the sum of the series with an error less than 1,000th, and of course we're able to apply the alternating series remainder theorem because we have a convergent alternating series. So we've looked at the alternating series remainder theorem and a couple of applications of it. So now we'll take a brief look at the proof that is in your textbook. So in this theorem, we have a convergent alternating series satisfying this condition. So that's given information. And we want to show that if that's the case, then the absolute value of the remainder R sub n in approximating the infinite sum by the nth partial sum is less than or equal to the first neglected term, as we have seen in our examples. So when you look at the proof here, here's what you should look for. So if you have a convergent alternating series and you delete the first n terms of the convergent alternating series, the remaining terms will also form a convergent alternating series. So that's what the first sentence states. The series obtained by deleting the first n terms of the given convergent alternating series will also be a convergent alternating series. So it will satisfy the conditions of the alternating series test, and it will have a sum that's equal to R sub n, because we're considering what happens when you delete the first n terms of the convergent alternating series. So the remaining the series of the remaining terms will be equal to the difference between the infinite sum and the deletion of the first n terms, which would be the nth partial sum. So basically the proof is trying to argue that if you put absolute value around that, that has to be less than or equal to the first neglected term. And that's basically what the proof is trying to show by using this mathematical reasoning. And the conclusion would be, consequently, the absolute value of the difference between the infinite sum and the nth partial sum has to be less than or equal to the first neglected term, which would establish the theorem. And again, the very first sentence is key for you to make sense of what's being shown here. Basically, you have a convergent alternating series, so if you subtract the first n terms, the remaining terms also form a convergent alternating series. And here we have R sub n is, of course, the difference between the infinite sum minus the first n terms that we're deleting. And we're just trying to show that the absolute value of that is less than or equal to the first neglected term. So now we look at the justification that is provided here. So let's look at the justification that is provided here. And here's what we have. So again, if you look at the notation, this is our convergent alternating series with infinitely many terms from n is equal to 1 to infinity. And then for the nth partial sum, we're subtracting the first n terms. So we're subtracting the first n terms of our infinite convergent alternating series. So from n is equal to 1 to n. So that's what we're doing there. And when you do that, you can think about why you can have this line in our proof next. You have to think about how the index will now start at n plus 1, So you will have negative 1 to the n plus 1, which is n plus 2, but negative 1 to the n plus 2 is the same as negative 1 to the n. So that's why you have that. And after you do that, the next step is just factoring out negative 1 to the n from each of these terms. And basically, all that is doing is giving you an alternation of signs. So you can simplify the notation by factoring this out from each term. And all this is saying is, whatever the sign of the first term is, you will have an alternation of signs in the terms that follow, because you have an alternating series. So that's the mathematical justification for that. And then we call this here, and the next thing is, let's look at the absolute value of that. So what happens when you look at the absolute value? Well, you no longer have negative signs anymore. You just have positive. And because of this particular condition from the hypothesis, we know that when we know that this is going to be a non-negative sum, because a sub n plus 1 is less than or equal to a sub n. So when you are subtracting a sub n plus 2 from a sub n plus 1, this quantity cannot be greater than the first one. So when you subtract, you're not going to get a negative value. It's going to be positive. So for that reason, we can write the absolute value because we know this is going to be positive. And all we did to make sure that it was positive was just get rid of this particular sign. If it had been negative, we would just get rid of that. So now you just group pairs of terms. Again, you're just factoring out a negative 1 from the first group. So you can see that when I factor out a negative 1 from the first term, I would have this. And each pair of terms that you have in the parentheses are going to be non-negative, again, because of this condition. Because any term that follows is going to be less than or equal to the preceding term. So when you do the subtraction here, that's going to be a non-negative quantity. So you're subtracting non-negative quantities. So what that means is the very first term here, since you're subtracting non-negative quantities that are in parentheses, after you subtract all of those non-negative quantities, if you keep going to infinity, if you're subtracting non-negative quantities from this one, the infinite sum has to be less than or equal to the very first term there, which is the first neglected term. So today we looked at objective 1, being able to approximate the sum of a convergent alternating series by using the nth partial sum, and using the alternating series remainder theorem to know the maximum possible error of our approximation. We looked at 2 variations of applying the problem with our 2 examples. We looked at 2 variations of applying the alternating series remainder theorem with our 2 examples.